There are important points about hydride addition to carbonyls that we need to remember. And number one is that sodium borohydride and ABH4 is not powerful enough to add to type 2. Type 2 is the ester, the acid chloride, the carboxylic acid, etc. It can only add, remember, to aldehydes and ketones. And then number two is if you add lithium aluminum hydride, which is a powerful reducing agent, it would add twice to the ester, even if one equivalent is used. So if you recall, this is basically what we did in the last reaction. Notice that we did not stop at the aldehyde. The reaction kept going until we ended with an alcohol, not the aldehyde. So this creates an opportunity for research by organic chemists to question whether there is a route that we can take to go from an ester to an aldehyde. And luckily there is. We have a compound called diisobutyl aluminum hydride. You don't have to know the structure, but it's 2-isobutyl alkyl groups attached to aluminum, and there's of course a hydrogen. This acts as a Lewis acid. Okay, so Lewis acids, if you remember, they accept electron pairs, an electron pair. And we just refer to it as Diisobutyl H. Diisobutyl H has this formula. This can take you, and I'm not going to go over the mechanism, this can take you directly to an aldehyde. So you went from an ester to an aldehyde. It's not a very efficient reaction, but it does the job. So remember, you need to remember this exclusively reduces esters to aldehydes. You have to remember this statement because we're going to need this for synthesis problems, of course. Now let's go to the next reaction we have here is that lithium aluminum hydride adds twice to acid chloride to give alcohols. So what I would like you to do is to pause my video and work out the mechanism for this. The only change we have here, the only change that I have here is I replaced the ester, the OCH3, the alkoxide group with Cl. So basically what's going to happen is that this mechanism will be the same, of course, taking into account the Cl now. So pause the video and work out the mechanism. And then when you're done, you can replay the video. Okay, so I hope you paused, but now I'm going to continue working on it. So here's we need to draw the lithium aluminum hydride. Okay, we have the CH3. Double bond, the pi bond breaks. And now we have Cl. And of course, we added an H. So we have a leaving group, just like in the ester as the alkoxide. So then these electrons are going to come down, kick the Cl out. Okay. Now we understand that aldehydes are less reactive than acid chloride, which is what we started with here. So we might expect this to stop here, but the reaction does not stop here. So lithium and aluminum hydride will react again. And of course, after adding water, you know how to protonate. Then you would end up with the alcohol, the primary alcohol. So lithium aluminum hydride is a very powerful reducing agent. It will not stop no matter what. It will stop with the alcohol because there are no more bonds to obviously break here anymore. So now what is the solution to that? What can we do? Well, we do have a solution. We use lithium tritert butoxy aluminum hydride. It's really, really a big molecule. This will ensure that you stop at the aldehyde. Once again, there's a mechanism that I'm not making you know it. So here we go. We can safely go from the acid chloride to the aldehyde.